Good evening, everyone. In the previous lecture, we discussed about the force on a charged particle, right? So we'll be continuing from there. We calculated the force on a charged particle as it was given by the Lorentz force, that's Q times V cross B, right? So the direction of the force was given by the cross product of velocity vector and the magnetic field vector, right? So that was a force on a charged particle because of uniform magnetic field, right? We discussed different cases as well, where we discussed that if the velocity vector is parallel to the magnetic field vector, then the cross product between the two vectors will be equal to 0. And in that case, the magnetic force on a charged particle will be 0, right? So the force on charged particle will be 0 in two cases. One is if the velocity vector is parallel to the magnetic field vector, or the velocity vector is anti-parallel to the magnetic field vector, right? In these two cases, the net magnetic force acting on a charged particle will be equal to 0, right? And then we also discussed about the maximum force on a charged particle in presence of uniform magnetic field is when there is angle between the velocity vector and the magnetic field vector is actually 90 degree. It means that the two vectors are perpendicular to each other. In that case, the magnetic force on a charged particle will be maximum, right? So let's discuss this short question here. The question is that a proton moving along z-axis, right, with constant velocity, right? If a magnetic field is applied along y-axis, then direction of magnetic force on proton, right? So along y-axis, there can be two directions, right? One, it can be along positive y-axis, it can be along negative y-axis, right? Let's assume that the direction of the magnetic forces are magnetic field is along plus y-axis and the proton is along plus z-axis, right? So we can write this velocity vector can be written as v vector. Here will be along magnitude v and it's along z-axis. Let's write it as k cap, right? And similarly, the magnetic field here is along y-axis. We can write b vector will be written as, let's suppose it's b naught. It's a uniform magnetic field and it's along y-axis. So b naught j cap, right? B naught j cap. Then direction of magnetic force on proton will be nothing. It will be v cross b, right? It will be given by v cross b. So it will be given by v cross b vector, right? So v cross b will be nothing. It will be v k cap cross b naught j cap, right? And we know that if this is I cap unit vector, this is j cap unit vector, this is k cap unit vector, then k cross, if we move in this circle in a clockwise direction, right, I cap cross j cap will be k cap, right? And similarly, if we move in the anti-clockwise direction, like j cap cross I cap, it will give us minus k cap. And similarly here, k cap cross j cap will give us minus I cap, right? So it means that v cross b will be actually minus v b naught I cap, right? So it means the magnetic force acting on this proton will be along negative x-axis, right? It will be along negative x-axis. So this will be the magnetic force on this proton, right? So the direction of the magnetic force will be along negative x-axis. Now moving to the next question, that from the path followed, you can see here there's a diagram given for the three particles, right? From the path followed, identify nature of charge on the particle, right? You can see here, this is a region of the magnetic field, and magnetic field is perpendicular to the plane of this paper, right? And into the plane, right? This is the magnetic force direction of the magnetic field, uniform magnetic field. And you can see there are three trajectories for three different particles given in this picture, right? This is particle 1, it's moving along this direction, and this particle 2, it's moving along this direction, and this is the particle 3 moving along along this path, right? You can see that the particle 2 is moving undeflected, right? It's moving undeflected. It means that since this particle is moving, right, it means that there is actually no magnetic force acting on it. The only possibility that the magnetic force on this particle 2 is 0, is that the charge on this particle should be zero, right? Or we can say that this particle 2 has to be a neutral particle, right? It will be an electrically neutral particle. That's the reason it moves undeflected, because if this particle contains some charge, then definitely there will be some magnetic force on it, and this particle is going to show some deflection, right? But this particle 2 does not show any deflection. It means the net charge on this particle is zero, or we can say that this particle is a neutral particle, right? So the charge on this particle is zero, right? And talking about the particle 1, right? So this particle 1 is moving along this direction, right? It means that if this particle is deflecting along this direction, it means that the force must be somewhere along this direction, right? Force must be along this direction. That's why the deflection is along this curve, right? So how can the deflection be along this direction, right? Let's suppose this is the velocity vector, right? This was the initial velocity vector, right? And this is the magnetic field vector. So V cross B, in this case, V cross B will be along upward direction, right? It means the force has to be in the upward direction, and if this is in the upward direction, it means that this particle has to be a positively charged particle, right? It will be positively charged particle, right? So the particle 1 will be positively charged and the particle 2 will be a neutral particle, right? And the particle 3, talking about the particle 3, since this particle 3 is moving, the velocity vector is along this direction. If this particle, suppose if this particle is a positively charged particle, right, then the force on this particle has to be along vertically upward direction, right? But this particle third is actually deflecting along this curve. It means that it's only possible if the force acting is along downward direction, and along downward direction it will be only possible when the charge on this third particle is actually a negative charge, right? Negative charge. The charge on this third particle has to be a negative charge. So it means that the nature of the three particle is that first particle is positively charged, and second particle is a neutral particle, and the third particle is negatively charged particle. So that's how we can find the nature of the charge on these particles, right? Using the concept of the magnetic force, or the deflection, or the deflection or the trajectory of these particles in presence of some external magnetic field, right? Now let's discuss different paths of charged particle in presence of external magnetic field, right? So for the case first is that let's suppose that we have this charged particle, right? This is the charged particle of charge q, right? This is the charged particle of charge q, and let's suppose this particle is moving along this direction, right? Along this direction, and the magnetic field is also along this direction, right? Along b. This is the direction of the velocity vector, right? V. Which means that the angle between the velocity vector and the magnetic field vector is actually zero, and there will be no magnetic force on this particle, right? And initially this particle was moving along this straight line path. It means the net force is equal to zero on this particle, and this particle will continue to move on this path, which was a straight line path. So in this case, if there is no any other force on this particle, right, or we can say neglecting all other forces like gravitational force and all other forces, then this particle will move along a straight line path. So for theta equal to 0 degree, the particle will move along a straight line path. Similarly, for theta equal to 180 degree, it means that the velocity vector and the magnetic field vector are anti-parallel to each other, right? So this is the direction of the magnetic field vector B, and this is the velocity vector V. So in that case also, we know that the force will be given by Q times V cross B, right? Q times V cross B. And V cross B will be equal to 0, because V cross B is VB sin theta, and V sine 180 degrees, once again 0, right? So sine of 180 degrees, once again 0. It means there will be no force on it as well. So it will continue to move along the same path that it was moving earlier, right? So the path of this particle will be a straight line path once again, right? So there are two conditions where the particle will have a straight line path. One, the velocity of the particle is parallel to the magnetic field, and the velocity of the particle is anti-parallel to the magnetic field. In that case, the particle will have a straight line path. Now let's discuss about the case number 2, right? Case number 2. The case 2 is that the angle between the velocity vector and the magnetic field vector is 90 degree, right? The angle between velocity vector and the magnetic field vector is 90 degrees. So this is the velocity vector and this is the magnetic field vector, right? and the angle between them is actually 90 degree, right? This is the 90-degree angle, right? So if this is the 90-degree angle, then the magnetic force on this particle will be QVB, right? QVB. And the direction of this magnetic field will be, magnetic force will be given by this V cross B. You can see that it means that the velocity force and the velocity vector are not perpendicular to each other, right? Velocity vector and the force vector are perpendicular to each other. Then the path of this particle will be a circular path, right? It will be a circular path. It means that this particle will follow a circular path here, right? So it will move along a circular trajectory, right? It will move along a circular trajectory, right? So this will be the trajectory of this particle, right? So the trajectory of this particle will be a circular trajectory, right? So this particle is going to move actually along a circular path, right? So for theta equal to 90 degree, the path of this particle will be a circular path, and this circle will be actually along like this, right? So this circle will be actually like this, right? This is how the circular path of this particle will be, right? So this is the circular path of this particle, right? So for theta equal to 90 degree, the path of this particle will be a circular path, right? So if path of this particle is a circular path, then the force that makes particle to move in a circular path is what we call a centripetal force, right? So the necessary centripetal force for this particle to move along a circular path is actually provided by this magnetic force, right? Is actually provided by this magnetic force. It means that QVB acts as the necessary centripetal force, right? Acts as the necessary centripetal force for this particle to move along a circular path, right? If QEB is a necessary centripetal force, and we know that centripetal force is nothing, it's given by mv square upon r, right? Where v is the velocity of that particle, speed of that particle, r is the radius of that particle, and centripetal force is always directed towards the center of the path and along the radius of that path, right? That's how the centripetal force is actually directed, and the centripetal force continuously changes its direction, right? As the velocity direction of the velocity changes, the direction of the centripetal force also changes, but it's always directed towards the center of that circular path, right? So we can substitute that QVB equal to mv square upon r, right? mv square upon r, mv square upon. So from here, v and v will get cancelled, right? From here, we will get the r, which is the radius of this circle. That will be equal to mv upon qb. So mv upon qb will be the radius of this particle, right? Which is moving in this circular path, right? So the radius of this particle will be, or the radius of this circular path will be m given by mv upon qb. So it means that the radius of that circular path will actually depend on the velocity of the particle. It will depend upon the charge of the particle, nature of the particle, right? Nature of the charge on the particle, right? And be the magnetic field, right? How much magnetic field we're actually applying. It means that if the magnetic field is stronger and stronger, then the radius of curvature will be actually very short, right? So for a high intense magnetic field, the path of that particle will be a circular path, but it will be of a shorter radius, right? You can see that R, if V and Q are constant, then R will be inversely proportional to the magnetic field, right? Inversely proportional to the magnetic field applied. So this will be the path of this particle, right? If this is the path of particle, right? If this is the path of this particle, it's moving along a circular path with a constant speed, that's v, right? Now let's try to calculate the time period, right? We can calculate the time period as well, right? So time period can be also calculated for this path, right? So time period will be equal to the circumference of that circular path divided by the speed, right? Circumference of that circular path is 2 pi r upon the speed, that's v, right? And we know that this radius comes out to be me upon qb, right? So it will be qbv, right? So this v and v will get cancelled, so it means that the time period of this circular path will be 2 pi m upon qb, right? 2 pi m upon qb. And similarly, we can find the frequency of this circular path, or frequency of this particle will be 1 upon time period, right? So this will be equal to qb upon 2 pi m, qb upon 2 pi m, right? This will be the frequency, right? This will be the frequency of this particle, right? Now calculating the angular frequency, that's omega, right? Omega. So angular frequency will be given by 2 pi times the frequency, right? The frequency is QB upon 2 pi m, right? It will be 2 pi multiplied by QB upon 2 pi m, right? 2 pi m. Now this 2 pi will get cancelled. We'll be left with angular frequency as QB by m, right? QB by m. So this is how we can calculate the angular frequency as well. So we calculate the time period of this particle. We calculate the what we call as radius of this particle, frequency, as well as angular frequency of this charged particle, right? Angular frequency of this charged particle as well, right? So this is how we can calculate different things for this particle, right? And similarly, we can also calculate the kinetic energy. So kinetic energy here in this case will not change, right? Initial kinetic energy for this particle, let's suppose that was equal to half mv square, right? Half mv square. Then this final kinetic energy will also be equal to half mv square, because you know that magnetic forces does no work, right? Magnetic forces does no work because magnetic forces are always perpendicular to the velocity vector, right? If all those forces which are perpendicular to the velocity vector, right, the work done or the power delivered to the velocity vector will be actually there will be which are perpendicular to the particle or path of the particle, and the work done will be zero, right? So there will be no displacement along the direction of the force, right? So in this case, the kinetic energy of this particle is not actually going to change. Kinetic energy of this particle will actually remain same. So the total kinetic energy before will be equal to the total kinetic energy after, right? So the only thing that will change here will be the velocity vector. The direction of the particle is going to change, right? So the kinetic energy will remain as half mv square, right? So let's discuss this question here. You can see in this picture, in this question here, we have three particles, right? One is proton, another is deuteron, and third particle is an alpha particle are moving perpendicular to the B. Then find the ratio of the radii if they are moving with same speed, with same kinetic, with same momentum, with same kinetic energy. And fourth one is through same accelerating potential, right? Through same accelerating potential, correct? So let's try to find, let's see how we'll try to solve this question, right? Let's look at the solution of this question, right? So you can see that we have to find the radius ratio of the radius of three particles. One is proton, another is neutron, and third one is an alpha particle, right? We know that proton has a charge of 1 unit, right? 1 unit charge, that's equal to 1.6 into 10 to the power minus 19 coulombs. That's the charge of this proton, right? Now talking about the neutron, what is neutron? Deuteron is actually an isotope of hydrogen atom, right? It's an isotope of hydrogen, right? So where it contains both proton in the nucleus as well as neutron, right? So we can say that the mass number of this deuteron is actually 2, right? Where it contains one neutron and one proton, right? While the proton has the mass number of 1, right? And then alpha particle. And for alpha particle is nothing. Alpha particle, we call it as helium nucleus, right? Alpha particle is nothing. We call it as helium nucleus, right? Or He2 positive, right? If we remove 2 electrons from the helium atom, we get the alpha particle, right? So the mass number of this alpha particle is also equal to mass number of this alpha particle is equal to mass number of helium. That's mass number of alpha particle is 4, right? And the charge of this alpha particle is actually 2 units, right? Particle is equal to 4 and charge is equal to 2 units, right? Charge is equal to 2 units. Now talking about the radius, radius is nothing. Radius is actually equal to mv upon qb, right? mv upon qb. mv upon qb. Now if they have the same speed, right, it means v is constant, right? If v is constant, a magnetic field is also a constant b, right? Now we're left with only the ratio m and q. In that case, for case first, if v is same, p is same, then the ratio r1 ratio, r2 ratio, right? Or we can say that r radius will be actually directly proportional to m upon q, right? M upon q, right? So it means that r1 will be actually equal to k times m, M is the mass of proton, that's of 1 unit, right? And the charge is also equal to 1 unit, right? Similarly, R2 is the mass of deuteron, that's of 2 units, and the charge of that deuteron is also equal to 1 unit because it contains 1 unit, 1 proton, right? And similarly, R3 will be equal to K times, right? The mass of alpha particle, that's of 4 units, and the charge is 2 units, so it will be 2 times K, right? 2 times K, correct. So the ratio of these three radius R1 ratio, R2 ratio, R3 will be nothing. It will be equal to 1 ratio 2 ratio 2, right? 1 ratio 2 ratio 2, right? So this will be the ratio of the radii of these particles, right? In case of alpha particle, we have a charge of in case of alpha particle, we have charge of 2 units and mass number equal to 4 units, right? In case of deuteron, we have charge of 1 unit and mass equal to 2 units, right? So this will be the ratio 1 ratio 2 ratio 2 will be the answer in case they have the same speed, right? In case they have the same speed, right? Similarly, similarly, if we want to try, if we want to find the ratio of the radius when these three particles are moving with the same momentum. So in that case, in that case, we can just write mv upon qb. Mv is the momentum, right? We can replace it with p, so it will be p upon qb, right? If they are moving with the same momentum and p is also same, then the ratio will be r1 ratio, r2 ratio, r3 will be actually a ratio of their charge, inversely proportional to the ratio of their charge. It means 1 upon q. For proton, it will be 1 ratio, and for deuteron, it will be ratio 1, and for alpha particle, it will be ratio 2. So this will be the ratio of their radii if they move with the same momentum. That's 1 ratio 1 ratio 2, right? And similarly, if they move with the same kinetic energy, we can replace this momentum we can replace with under root of 2m times kinetic energy Ke upon Qb, right? So here in this case, you can also find out the ratio of their radii by comparing their, since they have the same kinetic energy. So it means that their ratio will actually depend upon, it will be directly proportional to under root of m upon q, right? Under root of m upon q. So this is how you can find the ratio as well, right? So this is how you can compare the radii of three particles using three different quantities. We used first speed, then momentum, and then kinetic energy. And you can also use the accelerating potential as well, right? So kinetic energy of the charged particle is always equal to charge times the accelerating potential, right? So you can replace the kinetic energy here now using charge times the accelerating potential. Then you can also compare the radii of these three particles, right, to calculate the ratio of radii, right? Now let's discuss the third case, right? That's the very important case with respect to the path of the charged particle, right? The case is that when motion of a charge in uniform magnetic field, right? Magnetic field is a uniform field, right? It's constant in direction as well as in magnitude. Now, in the third case, if we project a particle, if the charge particle, right? This is the charge particle of charge Q. It's moving at an angle of theta. This theta angle can be either acute angle, it can be obtuse angle as well, right? So this is the direction of the velocity vector, and this is the direction of the magnetic field vector, right? So what will happen what will happen to this particle in the case where there is an angle between velocity vector and magnetic field vector other than 0 degree and 90 degree, right? So what we can do is that we can resolve this velocity vector into two components, right? Let's resolve this velocity vector into two components, right? This component will be the v sine component, right? This will be v sine of theta, and this component along magnetic field will be v cos theta, right? It will be v cos theta. So v cos theta is actually the component of this velocity vector along b, and v sine theta is the component of velocity vector along perpendicular to b. Now v sine theta will be the component of velocity vector which will be responsible for the force to be on this charged particle, right? Because of v cos theta component is parallel to the magnetic field vector. So because of v cos theta component, there will be no force, right? So we can say that because of v cos theta, magnetic force will be 0, right? Magnetic force is 0, right? Because it's parallel to the magnetic field vector, right? In that case, the magnetic force because of that component will be equal to 0, right? But the magnetic force will be only here because of the vertical component, right? That's V sin theta. We can see that Vy is equal to V sin theta, right? Correct? V sin theta. So because of V sin theta, there will be a magnetic force, and this V sin theta is perpendicular to B. So it means that because of this V sin theta, the particle will try to move in a circular path, right? But apart from that V sin theta component, there is also V cos theta component. It means that particle will try to move in a circular path, but it will also move horizontally. So in that case, the particle will actually move like this. So this is the trajectory of this particle, right? So it means that this charged particle will move along a helical path, right? Helical path. Helical path. Why does it move along a helical path? Because this V sin theta component tries to move it in a circular path, but V cos theta component drags this charged particle along the horizontal direction. So that's the reason it will move in a helical path. It will not move in a circular path. It will move in a helical path, right? Correct. So it will move in a helical path. Now, now the question is, what is the radius of this helix, right? What is the radius of this helix? We know that R is equal to mv upon qb, right? Mv upon qb. Now, the radius of this, where v is the velocity of the particle which is perpendicular to the magnetic field, right? V is the component of the velocity which is perpendicular to the magnetic field. Here, the component of velocity which is perpendicular to the magnetic field, it's the v sin theta. It means we have to replace this uh, v by vy, right? So it will be mv sin theta upon qb. So this will be the radius of this helix, right? So radius of this helix will be actually mv sin theta upon qb, right? And similarly, when we calculated the time period of the particle, it was equal to 2 pi m, right? Or we can calculate the time period of this particle, right? So time period will be actually equal to 2 pi r, right? Upon the vy, that's the vertical component of the velocity. That's v sin theta, right? V sin theta. It means that it will be 2 pi times. We can replace mv sin theta, right? Mv sin theta upon v sin theta into qb, right? V sin theta into qb. Now this mv sin theta and v sin theta will get cancelled. We'll be once again left with the same time period. That's 2 pi m upon qb. It means the time period of this motion will not actually change. It will remain a constant, right? It will remain a constant, correct? But time period does not change. Time period remains same, right? Now the question is that will the frequency of this particle change? No, frequency will not change. Frequency will also remain same, right? Kinetic energy will also remain same. Kinetic energy is not going to change. The only change here will be the particle is going to move in a helical path, right? Particle will move in a helical path, correct? So this is how we can calculate the radius of the particle, and the radius of this particle is also going to change. Now it will depend upon the component of the velocity which is perpendicular to the magnetic field, right? You can see here. Now radius of this path actually depends upon the component of the velocity which is perpendicular to the magnetic field, right? So it means that it will move in a helical path like this, right? It will move along a helical path like this, right? Now radius of circular path, right? We calculate the radius of the circular path as well, right? Radius of circular path, it was equal to r is equal to mv sin theta upon qb, right? Mv sin theta upon qb. So this is how we can calculate the radius of helical path, or we can write it as concretely as mvy, where vy is the vertical component of velocity upon qb. So this will be the radius of that circular path. So the radius of the circular path will not actually change, and time period, radius of circular path actually changes, but the time period of this circular path will not change. It will be once again 2 pi m upon qb, right? 2 pi m upon qb will be the time period, right? So the radius of circular path will be same, mvy by qb, and the time period will be 2 pi m upon qb, right? Now the question is pitch of helix, or what we call as pitch. how we define actually the pitch, right? So pitch is nothing, it's actually the horizontal distance traveled by this particle, right? This is the axis of helix, right? You can see here, this is the axis of helix, right? This is the axis of helix, right? It means this particle is also moving in a circular path, but continuously moving along a horizontal direction as well, right? So in a one complete time period, what will be the horizontal displacement, right? In one complete time period, how much will be the horizontal displacement for this particle? That's what we call as pitch of helix, right? So pitch of helix is nothing, it's the distance or the horizontal displacement, right, of this charged particle in one complete time period. That's what we call as pitch of helix, right? So it will be nothing. So pitch P will be nothing. It will be the uh, horizontal component of the velocity multiplied by the time period, right? It will be V cos theta multiplied by the time period T, right? Multiplied by the time period T. So time period T is actually V cos theta. Time period T is actually 2 pi m upon QB. So this formula will actually give us the helix of that uh, helical pitch of that helical path, right? So pitch is nothing, it's the horizontal distance traveled by the particle in one complete time period, right? When the path of this particle is actually helical, right? And helical path will be there when the angle between the velocity vector and the magnetic field vector is either acute or obtuse, right? In case of if the angle between the particle velocity vector of a particle and the magnetic field vector is 90 degrees, then the particle is going to move in a circular path, right? And there will be no change in the kinetic energy of that particle, right? Now let's try to solve a question on this, on the case third, right? The question is that a charge q comma m, right? The particle is having a charge q and mass m projected with velocity 3 I cap plus 4 j cap in external magnetic field which is directed along I cap direction, right, with a magnitude of 6. Now the question is find radius of this circular path, pitch, as well as the time period of this circular path, right? Time period of this circular path and pitch of this helix, right? You can see here, if we try to calculate the if we try to see whether this will be a helical path or not. Let's try to see it will be a helical path or not, right? So you can see that if we draw this vector, these vectors in this plane, right, these vectors in this plane, so 3 I cap plus 4 j cap, it will be a vector, in the first quadrant of this y-x plane, right? It will be a vector in the first quadrant of this y-x plane. So this vector will be the velocity vector, right, which will be equal to 3 I cap plus 4 j cap, right? 3 I cap plus 4 j cap, and the magnetic field is directed along positive x-axis, right? So this will be 6 I cap, right? That's our B. So it means clearly there is an angle which is actually an acute angle here between the magnetic field vector and the velocity vector. It means that it's definitely going to move in a helical path, right? This cos component of this velocity vector will drag this charge particle along the horizontal direction, and the vertical component of this velocity will actually make this particle to move in a circular path, right? Hence the path of this particle will be a helical path, right? Resultant path will be a helical path, right? So we can see here the vertical component of this velocity is actually equal to 4, right? And the horizontal component of this velocity is equal to 3, right? And the magnetic field has the magnitude of 6, right? Now let's try to find all these quantities. So radius of this particle was actually m vy upon qb. So this is the radius of this helix, right? So mass of this particle is m, right? Velocity is given as 4. Vertical component of the velocity, that's 4 upon the charge is q, and the magnetic field has a magnitude of 6. So it means it will be 2m upon 3q, right? So this will be the radius of this helical path, right? So this will be the radius of this helical path. So this is how the helix will be. So radius of this helical path will be actually 2m upon 3q. 2m upon 3q will be the radius of this helical path, right? So calculating now the pitch, right? Pitch P is nothing. It's the Vx, that's the horizontal component, right, of velocity multiplied with the time period, right? Right. So Vx is nothing. It's actually equal to 3, right? 3 times the time period, right? Time period, we know that it's 2 pi m upon Q times P, right? Q times P, and P has the value 6 here. So 6. So this 6 and 6 will get cancelled. We'll be left with the pitch as pi m upon Q, right? Pi m upon Q. The time period has to be equal to 2 pi m upon 6Q, right? 6Q. So it will be pi m upon 3Q. So this will be the time period of this particle, right? And this will be the helical path of this particle, right? So the conclusion is that when there is a magnetic field, external uniform magnetic field, then there are three paths possible for a charged particle. The path first is this straight line path. In the case when the angle between the velocity vector and magnetic field vector is either 0 degree or 180 degree. The case second is that the path of the particle can be a circular path in the case that angle between the velocity vector and the magnetic field vector is 90 degree, right? The third case is that if the angle between the velocity vector and magnetic field vector is acute angle or obtuse angle, right? In that case, the particle will move in a helical path, or we can say the trajectory of that particle will be a helix, right? And then we define different physical quantities. We define the pitch of helix, we define the radius of that helical path, right? So that radius will not actually change, right? The radius of that helical path is not going to change. It will remain same, right? And velocity is also not going to change. It will remain same because magnetic forces actually does no work, right? So energy is not going to change. The only thing that will change will be the path of this particle, right? The path of this particle will change, right? And radius will actually depend upon the vertical component of the velocity, right? Whatever be the vertical component of velocity, it will depend upon that. So radius will be given by mv by upon qb, right? So that's it with respect to the different paths per particle, right? Now let's discuss about a general Lorentz force, right? General Lorentz force. So sometimes it's not always possible. Sometimes there can be electric field as well, right? We in the previous lectures, in the last slide or the last lectures, we discussed that the only force that acts on the charged particle was a magnetic force, right? That was only possible if there is no presence of any external electric field in the region. Then the only force that can act on that particle in the presence of some external magnetic field will be a magnetic force, right? But in case where there is an electric field as well present in the region apart from the magnetic field, right? Then what will happen, right? In that case, there will be two forces acting on the particle. One will be the electromagnetic, one will be the electrostatic force, right? Electric force because of the presence of external electric field, and there will be another force that will be magnetic force. So the total force will be uh, electric force plus the magnetic force acting on the particle. So the net force actually in presence of external electric as well as magnetic field, the net force will be an electromagnetic force. There will be a magnetic force and there will be electric force as well. So electric force will be given by the charge multiplied by the electric field vector plus the magnetic force will be Q times V will be the velocity vector and P will be the magnetic field vector, right? So this is what we call as Lorentz force, right? This is the Lorentz force. This is the Lorentz force. So we can say that when a charged particle is moving in a region where there is both electric field vector and the magnetic field vector, right? Then both electric as well as magnetic forces act on it. The result of these two forces, what we call as electromagnetic force or Lorentz force, right? Still, we're assuming that there is no gravity on the charged particle, right? So this will be the resultant force on that charged particle, right? Now let's suppose that if this resultant force is zero, right? Then what is the possibility for this resultant force to be zero? If this force is substituted to be equal to zero, so in that case, the particle will move in a straight line path. The path of that particle is not going to change because the force on that particle is zero, right? Then we'll identify the condition for this particle to move along a straight line path only when there is both electric field as well as magnetic field present in the region, but the net force on that particle is actually equal to zero, or we can say that the electric force is actually cancelling out the magnetic force on the particle, right? So it means that QE will be QE plus Q times V cross P will be equal to zero, right? Will be equal to zero. right? This Q and Q will go, right? It means the electric field vector should be directed along minus V cross P, right? Minus V cross P. If this is the direction of the electric field vector, right? If this is the direction of the electric field vector, in that case, the net magnetic force, the net magnetic force or the net force acting on that charged particle can be zero, right? So E should be equal to minus V cross P, right? If this is the electric field vector, that's minus V cross P, that then in that case the net resultant force on that charged particle in presence of electric as well as magnetic field will be equal to zero, right? So this is how we can find the condition for the net electric and magnetic field to be equal to zero, right? So a particle moving with velocity v as shown in the figure, then the path of the trajectory and also find the effect on the speed, right? So you can see here that uh, the velocity vector of this particle is along the direction of the magnetic field vector. So velocity, if the velocity of the particle is along the direction of a magnetic field, in that case there will be no magnetic force. So we can say here that magnetic force on this particle F magnetic will be equal to zero, right? F magnetic will be equal to zero, right? So F magnetic here is zero, right? Now the second case, now there will be a force because of electric field as well, because charge is present here in the presence of extra electric field, right? There will be a electric force as well, right, on this particle, right? But this electric force, let's suppose that this is a positively charged particle, right? Plus Q, right? Then the electric force will be along the direction of this electric field, right? And this electric field vector and velocity vector is parallel to each other. It means that the electric force will be along the direction of velocity vector, right? Along the direction of the velocity vector. It means that the path of this particle is not going to still change, right? Because the velocity vector is parallel to the force vector, right? So in that case, the path of this particle will not change. It will be a straight line path as well, right? So it will be a still straight line path, right? So the particles will still, this charged particle will still move along a straight line path, right? Now, also find the effect on the speed, right? Effect on the speed. But definitely there will be effect on the speed of this particle, right? Because you know that now the net force acting on this particle is actually QE, right? This is the net force, right? Net force F net is actually equal to F electric plus F magnetic, right? F magnetic. And we know that this magnetic force is actually equal to zero, and the electric field only acting on this particle is QE, right? This is the net force. And the acceleration of this particle will be nothing. It will be the net external force upon the net mass of this charged particle, right? That's QE upon M, right? If this is the E is the uniform field, it means this charged particle will be moving with a constant acceleration or uniform acceleration, right? So the velocity of this particle after some time t will be actually, velocity of this particle after time t will be actually, that will be v is equal to u plus at, right? U plus at, that will be QE upon m multiplied by t. So this will be the final velocity at any time t for this charged particle, but the path of this particle will be still a straight line path, right? The path of this particle will not change, it will be a straight line path, right? But the speed of this particle will change because of the presence of external electric force, right? Or we can say that there will be a work done by this electric force, right? Or the kinetic energy of this charged particle is definitely going to change, right? Otherwise, in the case of magnetic forces, the magnetic forces does no work, it does not change the kinetic energy of the particle, right? Now let's move on to the next question here, right? A particle having charge plus 5 coulomb moves with velocity given as 3j meter per second in an electromagnetic field. If P is equal to 3I plus 2j Tesla, right? And the electric field vector is along a k cap direction, then find net electromagnetic force on that particle, right? So the net electromagnetic force will be nothing. Electromagnetic force will be nothing. It will be given by q times electric field vector, that will be electric force, then q times v cross p vector, that will be the magnetic force on this particle, right? So this will be the net what we call as electromagnetic force on this particle, right? So charge of this particle is given as 5 coulombs, so we'll write it as 5, right? Multiplied by the electric field, that's given as along 2 k cap, right? That will be twice k cap, right? plus 5 times V cross B, right? 5 times V cross B. So V is given as 3 times J cap, right? And crossed with 3 I cap plus 2 J cap, right? So it's crossed with 2 I cap, 3 I cap plus 2 J cap. It will be 10 K cap right here. So it will be now we know that J cross J is 0, right? We have to just do the cross product with J cross I cap, right? J cross I cap, and J cross I cap is nothing. It's actually minus K cap, right? J cross I cap is nothing. It's minus K cap, right? So it will be 5 times. That will be 3 into 3, right? That will be 9, right? And it will be a direction of minus K cap, right? Because J cross I actually gives us minus K cap, right? Minus K cap. So it will be 5 9 45, right? So it will be 10 K cap minus 45 K cap. So we'll be left with minus 35 K cap, right? So this will be the net or the resultant force acting on this charged particle, or we can say this is the resultant electromagnetic force on this charged particle, right? That's minus 35 K cap. It means it's along the negative direction of the Z axis, right? Z axis, right? So this will be the net electromagnetic force on this particle, right? I think we should stop here, right? In the next lecture, we'll be discussing about the magnetic forces on current carrying conductors as well, right? So this we'll be discussing in the next lecture, right? We'll stop here. We'll meet in the next lecture, right? So, so that's it for today. Let's meet in the next lecture. Take care and goodbye.